Hi, my name is Bailey Chambliss, and this is my Physics 2211 lab number 5, and for this lab I chose the Slinky drop video. So a brief introduction of this lab. The purpose of this lab was to measure and to model the motion of a Slinky dropped from static equilibrium as it drops to the ground, also to determine if the bottom of the Slinky model remains stationary before falling as it does in the video. So to analyze this, we started by using the tracker platform where we could determine the actual data values of the Slinky after it was dropped. To do this, we uploaded the video to the tracker software and then tracked the center of mass as it after the Slinky was dropped. And then it gave us some values for the initial conditions. So then we applied those to the starter code and the Python software, and we're able to model the same situation but under ideal conditions using the Python platform. And then we could use the results of both the tracker platform and the Python platform, compare them, and then come up with some conclusions. So a brief preview of our results. The results of the Python model and tracker data strongly resemble one another. In both models, the bottom of the Slinky remained stationary after the top of the Slinky was dropped until they met one another when the Slinky was dropped from static equilibrium until it reached its relaxed length, and then the bottom moved and they both reached the ground. So some of the key ideas under this lab are Newton's second law, which is that the final velocity of our object is equal to the initial velocity plus the net force divided by the mass times the change in time. Our net forces are the force of gravity, the force, like the drag force, and then the force of the Slinky. So for gravitational force, we have that W equals the negative mass times gravity times j hat, or the unit vector in the y direction, and then we can see that below. J hat equals direction 0, 1, 0, and that's what we have in our code. And then we have that the drag force, or FD, is equal to speed squared times v hat. So this is the model that was placed into tracker. As you can see, the Slinky starts expanded and then is dropped. So show that one more time. Oop. So for our tracker model, we put the center of like our coordinate system at the bottom of the Slinky when it was placed, like the initial video. And we have that our initial mass is 0.25 kilograms. Our initial position of the Slinky is 2.4 e to the negative 2 in the plus or the positive y direction. And then our initial velocity is 0 because the Slinky is at rest initially. And as you can see, we have our data to the right. So the next is our glow script model. We took those initial conditions that we got from the tracker model and then placed them into the glow script model to model our ideal conditions. And then after running that, we concluded that the data from the tracker model had a slightly steeper slope than the Python model because the spring force canceled out the force of gravity, so that means that some of our forces equal 0. The bottom of the Slinky remains motionless for some length of time. When the Slinky reaches its relaxed length, the net force is no longer equal to 0, so the bottom of the Slinky begins to move with the rest of the Slinky. So some potential sources of error include errors in the tracker or Python software, human error in tracker, and that can come from tracking the center of mass correctly or missing a point, misclicking. Some discrepancies in recording just because we weren't the ones to record this video, and other human error. Thank you.